Welcome, Mrs. Mahoney's podcast 4.2. We're at the bottom of page 2, well, 2, the second 2, and let's just do a couple of vocab words we're going to be using in this next podcast. Also, you need your note packet, obviously. Also find your periodic table to have in front of you as we get working through this, because I'm going to be referencing that a lot as we go through some of these trends. So our first vocab word, nuclear charge. That's just the attraction between the positive protons and that negative electrons. So when we talk about increasing that nuclear charge, weakening that nuclear charge, that's what I'm talking about, that attraction. Think of it like a magnet. Second word I'm going to be using, shielding. Okay, now don't panic on this screen. You really only need to write down what you have until the parentheses, unless the parentheses helps you to understand it, and then you can add that or put it in your own words. So the shielding is just kind of what it says. Those are our inner level electrons. They're the ones that are kind of putting a protection between that nuclear charge. It's going to weaken the nuclear charge. So they're going to put up a block between the positive protons and your outer shell or your valence electrons. Hence why they're called shielding. They kind of weaken that attraction. So if we talk about there's more shielding electrons, that means there's going to be less of that nuclear charge. And then the third one is just a lot of these trends. I'll be talking about a main group pattern, the main group trend, the main group trend. Make sure you know what I'm talking about when I say that main group trend. And there's different ways of saying it. These are really 3 different ways of saying exactly the same thing. You pick the way or find the way that sticks in your head that you know that if I'm talking about main group elements, you know which ones I'm talking about. They're your S&Ps, or looking on your periodic table, they're the ones that have the A's, 1A, 2A's, or all the other elements other than those transitions. Or you could even look at it. What's another way that we're looking at it? It's all the ones. So what is that number-wise? 1, 2, and then looking at your periodic tables, it would be groups 13 through 18. So whatever sticks in your head to when I'm talking about main group elements and when we talk about trends, so you can kind of visualize, that's what you need to do. Okay, in this section, we're going to be talking about different trends that we see within the periodic table, and you're going to have to be able to organize elements according to their trends, and you're also going to have to be explaining why you see the trend. So it's 2 parts. It's not just memorizing an arrow. We need to know a little bit more of why it's happening. So the first thing we're talking about is just the radius, the atomic radius. Well, the radius technically is defined as 1/2 the distance between the nucleus, or the nuclei, plural, of 2 atoms. You know what, for our purpose, it's fine to think of it as an atom's a circle, and the radius is still 1/2. Oops, it's just the same as a radius in geometry. It's the size. So if we're talking about the atomic radii, yes, we're talking about the size of the atom. So let's look at how they relate on the periodic table. Okay, so periodic trends. Remember, periods, this is saying going across the rows. So going across the rows, what kind of trends do I see? Well, here's your only one word you have to fill in there. So let's look at what this is saying, though. It's saying as I go across the row, because I'm putting the electrons, let's go across, let's just even the 2p's. As I go across, I have 1 electron, that's 2p1, 2p2, 2p3, 2p4, 2p5. All these electrons are going, remember, here's my tiny nucleus. I'll keep doing that. My tiny nucleus, since they're all going the same distance, what that's going to do is pull that tighter, make that nuclear charge increase. So what happens as you go across the period? They get smaller as you go from left to right, or you see a decrease in the size. That's what they're saying. It's decreasing size as you go that way because the electrons are going into the same energy level. Okay, what about as we go down a group then? Well, let's go down a group. Now we're being added to the higher energy levels. And so what happens? They're further from the nucleus. Let's go down group 1. Lithium. This electron is going to be in a 2s. Sodium, it's in a 3s. I'm talking about outer shell electrons again. This is in a 4s. That last electron here, 5s, 6s. Because remember, the higher the energy level means the further away from the nucleus. So look at this electron. It's way out here. Here's my nucleus. I think I learned not to press that so hard. So here, look at this. I'm farther away from that nucleus. That weakens that nuclear charge. So what happens? It can't pull it as tight, so they get bigger as you go down the group, because those electrons are going further and further away from the nucleus. And also what we get happening then is we get some of that shielding going on. Since all of these are full, I have all those 2p's, 3d's, they kind of throw a block from that positive nucleus. And because there's more shielding, that's decreasing that nuclear charge, that's just one more reason you see those electrons getting bigger as you go down. Now, kind of as you go across the period, you don't quite see it as much, but for us, we're just going to still assume you see the same trend. So we're not again going to focus on the exceptions during this. Most of our focus is going to be on the main groups. But if you see a transition element in there, still think of it as the trend, that they're going to get smaller that way. So we see a decrease. The reason, because they're going into the same energy level. And as you go down, you see an increase in size. And again, the reason now is because they're going into a higher energy level. So we had some questions here, okay? And this is where you need your periodic table in front of you. And this is how questions will show up on a test or on a quiz. So which of these would be the largest in radius? Find tin and strontium. My hint, look in period 5. So tin is clear over in group 14. Strontium is in group 2. Strontium is going to be the largest. It's furthest to the left, and it's also because it has less electrons in that same energy level. Okay, how about sodium and rubidium? Hint, group 1. Now we're looking at a group trend. So as you go down the group, rubidium's electrons are further away from the nucleus, therefore rubidium is going to have a larger atom. Okay, now we can look at more than one. Arsenic, nitrogen, fluorine. Find those guys. Hint, look in the P block. And again, I want the largest. We're looking at two trends, a group trend and a period trend. So these two are in the same period, but I know nitrogen would be bigger than fluorine. So fluorine's out. Now I have to compare these two because now all of a sudden it's in a group trend. So arsenic is actually going to be larger than nitrogen, so the largest of all of them is arsenic. Okay, I'm leaving you D and E to do, and then we'll check on that tomorrow to see what you found. So that's just the atomic radii. Okay, we can graph it. So when we graph it, and you're actually going to be looking at some of these graphs too, looking across here, look at what I have. This, lithium, sodium, potassium, rubidium, cesium, these are the actual data. They're increasing as you go down a group, and then this is going across the period. Look at how the radius decreases. Okay, here's where we get some weird little blips. Those are my transitions. That's where we said, okay, we're not going to worry about it. The general trend is the same. So sum it up. Here's this picture. You have this picture in it too. And again, look at your arrows. You can do it in arrows, but we need to know why. It decreases as you go across the group due to electrons in same energy level. So add also the reason. Okay, it increases as you go down to group because the electrons in higher energy levels. So it's the trend, but it's also the reason why we see the trends. Okay, that's the atomic radius. What about with an ions? Now remember with an ions, what we're looking at here, it's an ion, means it's has lost or gained electrons. So we're looking at comparing some sizes there of what happens. So if you remember, if the positive is a cation, remember the cat, the positive, it's a cation. Those are your metals. Well, what happens is it's losing electrons. So if it's losing electrons, you're going to increase that nuclear charge. It's going to make a smaller ion. So let's say, for example, calcium, if it's neutral, would be about this big. Well, if it's a calcium ion, it's lost 2, it's going to be smaller in comparison to its neutral atom. Well, hopefully that makes kind of sense. Thankfully, one of those things that isn't opposite, if you lose something, you lose weight, you're going to be becoming smaller. It loses electrons, it's going to be becoming smaller. Okay, how about the opposite then? Remember, negative is the anion. Those are your nonmetals. Okay, what happens now if you're putting in more electrons? You're going to weaken that nuclear charge, that attraction to the protons. So if it weakens it, it's going to be becoming bigger. So again, if I have just a nitrogen neutral, it's pretty good size. But a nitrogen, when it's an ion, has gained 3, it's going to greatly increase in size. So what you need to know, negatives are larger than their parent. And again, that should hopefully make some sense. If you gain weight, you're going to get bigger. Same thing with the ions. So you have some, just looking through that. And again, we're going to share, copy this, or excuse me, we have a copy of this to summarize the trends. But let's look at what you have in your packet. Which particle is going to be larger in size? Arsenide, that's an ion, or arsenic neutral. Arsenide, when it gains 3, will be larger. Therefore, it's going to be larger because it gained 3 electrons. Okay, look at this one. Fe plus 2, Fe plus 3. Well, plus 2 has lost 2, plus 3 has lost 3. The plus 2 will be larger. Okay, C and D I'm leaving for you. And again, we'll talk about those tomorrow in class as we get started. Okay, summarize trend. Now, 2 ways you kind of summarize. Let's look at it as far as one down the group. Look at the ionic radius is just like the atomic radius. So down the group, the nice thing is those two are exactly the same. Even though it's an ion, they get bigger as you go down a group, and they get smaller as you go across, as long as you're talking positives to negatives. But look at what happens here. Here's my neutral, and then here's my ion. But again, as you compare negative to negative, they're still getting smaller as you go across the period, and they get larger as you go down the group. So, a quick summary. This is smaller for the cation. The radius is smaller for a cation than it is for the parent ion. And when we're talking parent, I'm talking about the neutral. For an anion, it's the opposite. They get bigger when they're an anion than for the parent, again, neutral. But then the general trends is again the same as the atomic, the neutral atom. You're going to see an increase. You're going to see an increase as you go down. But then you see, so they get larger, increase. And then you see a decrease. So whatever, again, how you ever see of it, it's decreasing as you go this way. One way I kind of keep it in mind, I think, okay, helium up here is my smallest. Francium down here would be the largest. And then I know all the trends are going towards that when I kind of put it in perspective. Okay, the second trend, the next trend we're looking about today, and we do have one more we're going to be talking about the next day, we're talking about ionization energy. And part of the time with these trends, you need to know what the definition is. You need to know what it is. Ionization energy, the energy required to remove one electron, hence to make an ion. Let's get to where we're not just memorizing arrows. We know what it means, because if we know what it means, it makes the trends make so much more sense. So here's my neutral atom. I'm going to have some energy. I produce an ion, and then again, this electron's going to be free to make a compound. So it says write the equation for it. This is what it would look like. Take your neutral sodium. It takes some energy. You make a sodium ion, and you get an electron free. Let's look at across the period then. As you're going across the period, well, as they're getting smaller, that attraction is getting stronger, so it's going to be more difficult to remove the electron. That means you see an increase in the ionization energy as you go across the period, because it's going to take more energy to remove that. Well, look at these guys are noble gases. They want to gain electrons. They don't want to lose them, so it's going to take a lot of energy to remove them, especially those noble gases. They really don't want to lose an electron. It's going to take a lot of energy. Okay, going down a group. Same reason as the size. Since those electrons are going further and further away, it has a weaker charge. They're not being held as tight. They're easier to remove as you go down a period. Therefore, it's going to take less energy. So therefore, if it's less energy, they're easier to make an ion. You see a lower ionization energy. Now, same thing, transition energies, you see a kind of a weird little blip in the system. Actually, you see a reverse of that because of shielding, and I'm just saying this happens, but let's focus on the main group, and we're not going to focus on the exceptions. So still treat the transition metals as they're part of the main group. If you get something thrown in there, hopefully they're going to avoid the transition metals, but just in case, treat it like the trend. So again, we have some comparison. And again, first thing when you're doing this, you have to get yourself ordered in your head. Are they asking for lowest or highest? How are they asking me to arrange this? So right now I just want to know which has the lowest first ionization. So nitrogen or oxygen? You can say, okay, how are these related? They're in the same period. So therefore, nitrogen is going to be a little bit bigger. Its electrons aren't held quite as tightly. It's going to have a lower first ionization energy. Neon or fluorine, they're very close together. Neon has a full shell. It really doesn't want to lose it. It's going to have a higher ionization energy, therefore the lowest ionization energy. Okay, and this first just means to remove the first electron. That's all that's saying, which is what we're talking about, is to remove one electron. Fluorine or chlorine. Fluorine is smaller, holding onto it tighter, therefore chlorine will have the lowest ionization energy. Okay, I'm also leaving for you D and E, and then we'll come back and we'll talk about this tomorrow in class. See you tomorrow.